All right, hi everyone. Thanks for joining for today's IEDE Research Webinar. So today we've got Andrew, who's going to be giving his presentation, which is called Using Regression Models to Predict Urban Soundscape Perception. So it'll be around 40 minutes presentation, and then there'll be time for questions and discussions, and you can put your questions in the chat as we go through, or put them at the end, or you can use your raise a hand feature to ask the question. So I'll hand over to Andrew.
Yep, thanks, Phil. And yeah, I've tried to time it to 30 to 40 minutes. If I start going over, yeah, just interrupt me, let me know. Let's see if presentation will work. Okay, can you see my slides there? Cool. Okay, so hi, I'm Andrew Mitchell. For those who don't know me, I'm a final year, or I guess fourth year PhD student in the Soundscape Indices group. And so today I'm going to be talking about predictive modeling for urban soundscape perception. So real quickly, just to give you an idea of what to expect, I'm going to open up with a general introduction to what is soundscape and how do we measure sound perception. So what exactly are we trying to predict? How do we measure it? And then what do we try to predict? How do we make use of soundscape in engineering and design? And then I'll talk about our specific data set and what we're working with to do the modeling. And then I'll present a case study of why we are using this sort of predictive model in a perception-based thing. And I'll use the COVID-19 lockdowns, a paper that we've recently submitted as a case study for that. And then I'll talk about sort of where SSID goes from there and what's next in our modeling. So first up, let's start with what is soundscape? You know, what are we actually talking about? So we start with a background in noise pollution. The decibel in urban noise pollution is the most commonly used index, but it's an energy index. It talks about the physical energy within the sound, but it's not well correlated with human perception, and its applicability relating to regulations has recently been in serious doubt. So efforts to improve this include things like adjusting level requirements, sound level requirements for different types of noise sources or different contexts. For instance, one example from some of my past work was dealing with wind farm noise to properties. They had a lower sound level limit if a property is financially involved because they can accept a lower energy limit. But that is sort of just an ad hoc thing. And these efforts are still concentrated on noise control of let's make sure that the noise level is lower to improve people's health outcomes, rather than on designing overall environments. And moving away from this noise control focus involves treating sound as a resource as opposed to merely a nuisance. Smart city design should focus on improving the quality of life, which has been shown to be heavily driven by perception as opposed to strictly noise levels. So soundscape is sort of an attempt to take us away from this decibel noise-focused approach to a more holistic way of talking about the sound environment. And so that brings us to the sort of formal definition of soundscape, which is the acoustic environment as perceived or experienced and or understood by a person or people in context, which is a bit of a clunky definition, but essentially what it's saying is we're taking the entirety of the acoustic environment that people are exposed to in whatever space you're talking about, incorporating into that how people, the context of it, where the space is, how people perceive it, and focusing on that, on how people perceive it. And so quite a few different things go into that. As I said, we've got the context, we've got the sound sources, which make up the acoustic environment. That elicits an auditory sensation in the person who's exposed to it, which then gets interpreted by that person. And they bring in their own personal attributes to that, their own personal semantic information, meaning given to the different sources, and then they have some sort of response. And the outcome of that response is what we are trying to measure in Soundscape. But how do we measure it? How do we measure that perception? How do we talk about it? So this brings us to the model that we currently work with, and I'm going to be talking you through this figure. This is called the Circumplex model of soundscape perception. It was work done in 2010, where they were trying to figure out how do we formalize people's perceptual descriptions of the soundscape. And so they started out by asking people to rate this list of something like 120, I think, adjectives for various soundscapes that were played to them. So some complex urban soundscapes that were played to people in a lab, and they were asked on a scale, I think it was a scale of 1 to 5, rate them on these different adjectives. They then did a principal components analysis to work out how all these adjectives relate to each other and derive the principal ones, the dominant components. And so we can see a couple of things here. In the first component, we see that all those adjectives sort of center around the pleasantness or the attractiveness of the sound, right? And then on the other side, we come to annoying. So we've got this x-axis where positive is pleasant, negative is annoying. We then come up to a y-axis where orthogonal to that pleasantness is the eventfulness of the sound, right? And correspondingly uneventfulness on the other side. And theoretically, what this is saying is those two attributes are orthogonal to each other. They're not necessarily, they don't correlate with each other. And so that means you can have these combinations of this pleasantness and eventfulness. And here we have an example where if it's a pleasant sound which is uneventful, that combination, it's described as calm. And likewise on the other side, if it's unpleasant and eventful, it's chaotic. And we just keep moving around these different combinations and end up with a simplified version of this, where we can talk in 2 dimensions of all these different attributes are some combination of pleasantness and eventfulness. And this really helps us sort of formalize how we talk about the perception of a given sound. And that has been super useful to us. It's this sort of more quantitative, formalized way of talking about it. But then how do we make use of this perception in engineering and design? Because most soundscape research so far has focused on these appropriate methods of characterizing the existing soundscape of a space. And this is what the Circumplex model aims to achieve. But considerations for applying soundscape to noise mitigation practice are that at the moment, all of this relies on collecting surveys in person. So we go out to an urban space and we collect a survey in person, but that's not always possible. It's limited to this sort of post hoc assessment of an existing environment. So, you know, we go to a space which already exists and we ask people how they currently perceive the soundscape in this space. But then how do we apply that to proposed spaces? How do we say this space that we're designing will likely have this soundscape? That's quite difficult to do. And so that sort of brings us to the SSID project, which has 2 main goals. The first is to more easily enable soundscape characterization, that sort of post hoc that we've been talking about. And particularly which can allow us to more efficiently characterize many different spaces, because typically these past methods have been focused on just a few spaces, characterizing just a few spaces. And then the second goal of the SSID project is, or at least of my research within the SSID project, is to help develop soundscape for the design of spaces. And for this, we need some predictive soundscape modeling, because that is how we can determine the soundscape impact of a proposed design or of a new space. And for that, we need a model which can predict soundscape assessments based on objective and predictable factors. And so we have sort of 3 main requirements of this index, of this sort of predictive way of doing it. It should be based on objective or measurable factors. It should be generalizable to many different types of spaces, not necessarily just the types of spaces that we've already looked at. And it should be practical to implement without an excessive time or labor cost. So all of that sort of goes into this goal of let's create some sort of model which can tell us how a soundscape is likely to be perceived based off of measurements, using that circumplex, that circumplex dimensions that I talked about. So the first step of this was developing the Soundscape database, the Soundscape index database and model, and protocol. In order to build the model, we need a large, ideally multinational database of soundscape assessments in many different spaces. These assessments needed to be performed in situ because all that contextual information is kind of dependent on being in the real world space, being exposed to all these different things which will influence your eventual soundscape perception. And it needs to be organized with detailed metadata to enable us to link all of our multiple data streams together, because we're collecting a whole bunch of multi-dimensional stuff. We're collecting, well, I'll be talking about what we're collecting in a second. So to do this, we developed the SSID protocol, which is based on repeated questionnaires and is relatively simple and easy to carry out at multiple sites with hopefully minimal hassle. So I'll talk you through our survey, our questionnaires, briefly. So since our goal is to characterize this multi-dimensional thing in all of these spaces, we have quite a few different data points that we're collecting. The first is, I should say, in all of this, we are setting up in urban spaces, a lot of them around here and around London, something like a park or a square or like next to a street or something like that. And we stop people who are passing through and using that space, and we ask them to do a questionnaire to participate in our survey. And so each of these surveys includes a questionnaire that the person fills out, which I'll explain in more detail in a second. Audio recording for each group of respondents. So if we stop a couple that's passing through, we'll have them fill out the questionnaire together, and we'll take an audio recording while they're filling it out. So we get sort of exactly what sound they were exposed to while they were saying, this is my soundscape perception. We have continuous sound level meter measurements, which give us sort of the background level across a standard calibrated background level of the space that we were in. Similarly, we have continuous environmental measurements, taking things like temperature, humidity, and light levels. We have 360-degree photos so that we can capture things about the visual aspects of the space, like the amount of greenness in it or the number of people in the space, because all of those have been shown previously to potentially influence soundscape perception. And then finally, I'm not going to be discussing the rest of this presentation, but we were also collecting data to be used in lab-based experiments in virtual reality. So we have 360-degree video and essentially 360-degree spatial audio. So the questionnaire portion of that, I should say, so all of this survey data is organized in quite a particular way to help us better capture all these different things that go into soundscape perception. And so we organize it at the individual level, which includes the person's questionnaire. It includes the recording that was taken while they were answering their questionnaire. It might include a photo taken at the same time, etc. We then have a session level, because in order to capture the 100 questionnaires per location that we needed, we had to repeat this over multiple sessions, so multiple days. And that may have different environmental characteristics, different visual characteristics for that day versus a previous day. Then we have the location level. This all gets wrapped up into these questionnaires, and this data belongs to this location, and this data belongs to another location. And then to give you some idea of what questions we're asking, the most important, and again, what I'll be talking about later, are all those perceptual attributes that make up the Circumplex. So the pleasantness, vibrancy, eventfulness, chaoticness, and going all the way around it. So we asked each of those individually, and then we can collapse those into our two primary components. We can ask each of those attributes individually and then extract the overall pleasantness and the overall eventfulness of the soundscape. We also ask things about sound sources and overall how people perceive it. Do they feel that the sound environment was appropriate for the place that they were in? But I won't be discussing those in more detail for the rest of the presentation. But just so you know that those are in there. So that's a lot of stuff. It is quite a detailed protocol, but to hopefully give you an idea of the sort of spaces that we're looking at and what sort of data we were collecting, I've got some videos of the locations that we were working in that we did these questionnaires. So hopefully you can get a better idea of what we're actually looking at. So this one is taken in outside of the Tate Modern. You can kind of imagine you're sitting there in that nice green space outside the Tate Modern. We then stop you and ask you to fill out our questionnaire. And so you can picture yourself sitting there and listening to that sound and how you would fill out those various attributes. We then have an example in Regents Park. This is next to the Japanese garden. So still a very nice, potentially location, but quite a different soundscape, I would say. And then finally, we have right outside here at Euston Tap on Euston Road. I don't think this one will be too loud, but maybe a bit of a warning. Okay. So just some brief idea of what sort of locations we were at. And again, you can picture yourself if you were filling out those various attributes, pleasant, vibrant, chaotic, calm, how would you have assessed those particular locations? So all of that data collection, all those questionnaires and surveys were conducted during 2019, thankfully. And we ended up with 13 locations, 11 in London and 2 in Venice. Which also include these 360-degree videos and spatial audio. We were able to collect 1,318 questionnaires and 693 audio recordings, 30 seconds long, which go along with each of those questionnaires. And again, the reason that it's about half as many audio recordings as questionnaires is generally people were stopped in groups, and because they're filling it out at the same time, we only need one recording for multiple people to be able to match up the audio with exactly what their perceptual response was. So that brings us to the second half of this project and this work, which is a case study of an application of the modeling that we're talking about and how we actually made use of all this data. So as we all know, in 2020, we had the first of the UK's lockdowns due to COVID-19, which resulted in massive changes in our urban environments, right? We had restricted movement, no public gatherings, social distancing, and generally very restricted traffic. So our research question looking at this was, how did this change impact the soundscape of public spaces? So we have this whole data collection we did the year before of all these different public spaces in London and Venice. What can we do to investigate how that soundscape would have changed for people? The problem is we can't ask anyone, either because there's no one in these spaces or just because it was illegal to stop people on the street and ask them. So we repeated our recordings during 2020 during the lockdown in the same 13 locations, but we couldn't have the video and audio recording and the 360-degree video and spatial audio, and we can't have any questionnaire responses. So we can't use traditional methods of soundscape assessment to say this is how people perceive these spaces. But we could collect 608 audio recordings done in exactly the same way as we had done before. Tian Oberman primarily was able to go out to these spaces during lockdown and make the same recordings again. So we therefore need to build a predictive model to link the features of the recordings to what the perception of these spaces would have been. So the way we do this is we've got our 693 2019 recordings with their corresponding perception. We analyze them, we build a model to predict the perception, and then we apply that model to the lockdown recordings so that we can get the predicted perception of how people would have perceived it during lockdown. So we start with analyzing or extracting acoustic features of these audio recordings. I'm not going to go into a whole bunch of detail of all these different things, but feel free to ask more about these different features. Essentially, all of these are trying to extract different parts, different features of the sound. So on the left, we've got traditional acoustic features, the decibel, energy level, equivalent energy level decibel, a feature which characterizes the amount of low frequency content, and then a feature which characterizes the degree of variation. So how much does the sound level change over the time period of the recording? On the right, we've got the psychoacoustic features, perceived loudness, sharpness, which is like the amount of high frequency content, fluctuation strength, roughness, and tonality. Again, I won't be able to explain all of them, but we can extract all of these features characterizing different parts of the sound from the audio recordings and feed those into our model. So let's start with a pretty simple way of looking at this, which is let's just do a correlation between the decibel level, how loud is it, and the assessed pleasantness. And we can see when we plot this at the individual level, we've got some relationship between higher sound level resulting in lower pleasantness. That's what we would expect. The problem comes when you break this down by location. So when we analyze it by location, we can actually see that this relationship doesn't hold for every location, right? Only 3 of them actually have that negative correlation. The others have no correlation or have approaching a positive one. What does that mean? It means that all of these contextual factors of what location you're in changes the relationship between the acoustic feature and your perception of the overall soundscape. So doing sort of just a simple linear regression model doesn't really work because it's trying to analyze it across all locations at once and doesn't take into account these different relationships according to the location. So what's the solution to this? It's a multi-level model, right? So a multi-level model is a regression model that can allow us to incorporate these location level differences. So to build our multi-level model, we need to, I suppose I should say a little bit more clearly, a multi-level model is essentially a linear regression model that allows the regression coefficients, the slope coefficients, to change depending on, in our case, the location. And so we'll hopefully make that a bit clearer in just a minute. So our first step to building this is to determine the model structure. So we're building a model based on our acoustic features as input, which allows the relationship between these acoustic features and the outcome to vary depending on the location. We then set up the model with all the potential features included. And so this is our, the way that we would write this model in R, which is what I did. I did the modeling in. And so we're trying to predict the pleasantness and the eventfulness, because eventually we want to be able to plot a soundscape assessment on that 2-dimensional circumplex, right? So we can treat it as a coordinate plane and plot on that. So we're trying to predict the X and Y in that circumplex. So that's our outcome. We then have our full set of features. So I've only written 2 of them here, but we include all of our features at the start. And this is what's called the fixed effects levels. These are effects which are fixed across locations. So we're combining both within the same model features which are not dependent on location, and then we have features which vary by the location index or the location identifier. And so we again include all of our features in a structure which allows those coefficients to vary according to location, as well as being fixed across all locations. We then want to reduce all those features because we don't want all of them to be in there. So we need to do a feature selection. And so we do stepwise feature selection, where we begin with that full model we said with all features included. We then try removing each feature one at a time from the location level first. So to sort of illustrate a bit more, if we go back to our equation here on this level, which allows things to vary by location, we have loudness and roughness and sharpness and tonality and all these different features. We fit a model with all of them, and then we fit a model without, say, loudness and score it. We then put loudness back in and then move on and remove roughness and score it. And whichever one performs the worst, we discard that feature and we move on and continue this process. So we continue until no performance improvement is seen using the Akaike information criterion, which we use because it penalizes complex models essentially. So it's pushing us towards a simpler and simpler model. We do that until we see no performance improvement, and then we repeat that process at the fixed effects level, right? So we've reduced it at that group level, the location level. We continue and do that at the fixed effects level as well. And that finally, once we see no performance improvement, we get our final model structure and our reduced features. So this is what we ended up with for pleasantness. So we did this process separately for predicting pleasantness and for predicting eventfulness. And to sort of walk through what this means, here we end up with just, this is the symbol for loudness, psychoacoustic loudness. So just loudness has a negative coefficient, which is not dependent on location. So across all locations, there is a negative correlation, a negative coefficient for loudness. As it gets louder, it gets less pleasant. But then we move to that location level. And this is essentially what I was saying about allowing coefficients to vary depending on what the location is. So we can go across here and see at Torrington Square, we have this set of coefficients for our 3 different features here, which are characterizing the variation across time, again, characterizing the physical energy level of the sound, the decibels, and then characterizing the low frequency content. We can see Torrington Square here has a different set of coefficients compared to, for instance, San Marcos Square, right? And so it's able to capture in a single model, it's able to capture how all those relationships depend on which location you're in. So that's our pleasantness model, which is location dependent and is primarily dependent on some aspect of the loudness of the sound. We then move on to our eventfulness model, which is special because it's actually not a multi-level model. The feature selection reduced down and said location just isn't crucial here. So the feature selection removed all the features at that location level and still saw an improvement, and then eventually removed that second level entirely and saw an improvement. So here we just have a flat multivariable linear regression. So you can view this as, quite simply, eventfulness equals minus 0.08 times the sharpness value plus minus 0.02 times the fluctuation strength value, and we just continue on. And that was a huge finding for this modeling. it was very unexpected to see that there wasn't any dependence within this data set on what location you're in. So eventfulness is just driven, in this case, by the acoustic features. Yeah, so we then fit these two final models on our test data and score it to see how well do these perform. So we used an 80-20 training testing split to make sure that we weren't overfitting the model, and this was randomized evenly across locations. So we did the randomization within each location to make sure that we didn't end up, say, with like no instances of a particular location in the testing data. And then we evaluate it. And we do this in two ways. One is by evaluating its performance at that sort of base level prediction, right? So we're predicting the likely soundscape perception for an individual recording, right? And that's what we've plotted here. The actual, on the left, the actual response and the predicted against the predicted response for the training set. And then we calculate the mean average error for each of those predictions. And so this does, because the training and testing set mean average errors are quite close, we can see that we're not overfitting, which that's quite good. But when we move on to actually using this model, we don't actually care about that. We're not trying to predict the soundscape of an individual or an individual recording. We're trying to talk about the location as a whole. And so to do this and to score how well we're doing in that sense, we then, after fitting the model, we calculate the average response within each location, the average predicted response for each location. And we calculate the R squared of those average predicted responses across locations. We end up with an R squared test for pleasantness of 0.85 and an R squared test for eventfulness of 0.72, which, for context, is very good in the soundscape field, particularly for such a wide array of locations. So that, again, that's quite a lot packed in there. Hopefully you've been able to follow that. Questions on that sort of stuff are great at the end. So we then move on to the actual application. So we apply this prediction to I'm not moving forward, to lockdown data. So we run the calculated acoustic features from the 608 lockdown recordings through the model. So these weren't used in training at all. So the testing and training set were an 80-20 split of just the 2019 data, because that's the only one that we had, a labeled data set for. We had perceptual responses for. So now we want to actually use this model in order to figure out how would people have responded to the spaces during lockdown using the audio recordings. So we run the acoustic features through the lockdown audio recordings. Again, we calculate the average predicted response within each location. And then we can plot that predicted response on the circumplex axis. Using pleasantness and eventfulness as an XY, we can put a coordinate point within that axis. So just a reminder, this is what our soundscape circumplex looks like. We're treating pleasantness here as a positive to negative XY or x-axis, and eventfulness as our y-axis. So we're going to plot points as a coordinate within these two dimensions. So this is what it looks like for the 2019 responses, the actual responses that we were able to collect. And so we can see a few things here. We can see, one, this is our origin. So this is completely neutral right here in the sort of bottom left of this plot. So most of our locations fit up in the top right quadrant. And we can see some things that we expect, right? Camden Town and Euston Tap are in the annoying half of the plot, right? Which is exactly what we might expect. They're traffic heavy, they're quite loud, all that sort of stuff. On the other end, Regents Park Japan and Regents Park Field and Russell Square are all quite pleasant and generally down towards calmness. whereas things like Tate Modern, which had a lot of people in it, are assessed as vibrant. So hopefully you've sort of got that picture in your head of how we're characterizing these spaces and plotting them here. Because we then take our predicted responses from what came out of the models for the lockdown data, and we plot those. And I've added the arrows here to indicate how each location changed from 2019. So for an example, we've got San Marcos starting up here and the same place on this plot, and it moved all the way down into a calm, into the calm quadrant. So with that, we can take those changes, because that's what we really care about. We really care about how all these spaces changed because of the lockdown restrictions. So we can take those arrows and treat them as like a movement vector and recenter all those arrows on 0 on the origin and talk about the relative changes, how they all changed relative to each other. So that's what this plot shows. And we're gonna step through and talk about all these changes, because there were some really interesting things due to these massive restrictions during lockdown. So the first most obvious one is San Marco, right? So this is San Marco Square in Venice. And in 2019, we did the assessments during Carnival. So it was a huge crowds of people. It was packed. There was music. It was incredibly vibrant. And if we remember back to our 2019 here, San Marco is squarely in the vibrant quadrant. It's the most vibrant space. So due to the lockdown, we see a massive change to less eventful. We've removed all those people. It's now less eventful, but it's also quieter probably. So it has become more pleasant. So San Marco had a massive shift down to being more pleasant and less eventful. And it has the biggest shift because it was that massive change from being Carnival to being empty. And see this group here of Euston Tap, Camden Town, Torrington Square, and Pancras Lock, which all changed, with the exception of Euston Tap, all changed to be more calm, but also they're the only locations which really became more pleasant other than San Marco. And the reason for this is they were all dominated by some form of traffic noise in 2019. Pancras Lock is kind of the odd one out because it wasn't car traffic, it was actually rail traffic, because it's down there next to St. Pancras. But that's kind of what we would expect. During lockdown, there's much less road traffic, much less of all sort of traffic. Our recordings then capture that, and they're predicted to become more pleasant as the traffic decreases. We then have this other group, which actually became less pleasant, right? Pretty much everywhere became less eventful, but this group became less pleasant, which is a little counterintuitive. We've reduced urban noise. Surely, all of these levels became quieter. Surely they should all become better, but that's not actually what we're getting. And this is because these locations were originally in 2019 a mix of human and natural sounds. So that's what was dominant. And we've removed that human sound during the lockdown. And so that has made them become less vibrant, because vibrancy is associated with human presence and human sounds. And then, so yeah, that sort of breaks a little bit of what we might expect to see in a noise pollution sort of sense. If we've reduced the sound, it should get better, but that's not what we're actually getting. So finally, we have Monumento Garibaldi, which is this sort of quite quiet park with a gravel walk in Venice. And this one's particularly interesting because in the first of our recording sessions during 2020, during the lockdown, there were landscaping works. So we had a streamer going. Because of that, the researcher then went back, I think the next day, to do it again and get a more representative recording. But we ran both of those through the model. And the arrow in gray, which is up at the top left, is the predicted response with that landscaping work. Whereas the one in the bottom left was the repeated measurement without that landscaping work. And we can see that the model has picked that up very well. Even though the model was built without seeing any landscaping works, it doesn't know that that's what those acoustic features are there. And it can say, with that landscaping work, this space became much more chaotic. Whereas the session without that landscaping work, it fits right in with all the other natural dominated locations, which was actually a happy little accident of our measurements. So our key takeaways here are the modeling works and it's useful. We're able to capture the expected changes in perception within a wide variety of location types. Location context effects are very important for pleasantness perception, but not necessarily for the eventfulness axis. And a reduction in sound level, which pretty much every location saw, does not always lead to an increase in pleasantness. The accompanying change in the sound source composition is also important. And finally, the main takeaway is that this predictive modeling, which allows us to investigate things we couldn't do with more traditional soundscape methods, is an important tool for future soundscape design and assessment. So very briefly, what's next for this research? Where are we going from here? The first is generalization. Right now, we can only build and run these models for the specific locations that we've already characterized, right? So we could only do this predictiveness by saying we're back at the same location. So we want to replace that location ID with things which characterize location, like visual characteristics, architectural typology, and uses, so that that can then be spread out to new locations which share features with what we've already done. We want to incorporate environmental and visual features and see how those impact and interact with things like the sound level. We've already done some work on this, but this is specifically a linear model. So how much better could we get if we had a nonlinear approach? Right now, the evidence suggests that we're actually doing quite well with the linear, and we may not see a benefit with nonlinear approaches. And then finally, I want to transition to using Bayesian methods so that we're, rather than discussing like a single point of predicted response, we're talking about a distribution of the likely responses, because that better encapsulates the randomness that's present in people's actual perception. And then ongoing work is to simplify how we talk about this, because this sort of coordinate space, circumplex stuff can get, I'm sure you guys have felt, it can be a little bit hard to grasp, particularly right off the bat. So that's it for me. Thank you very much for your attention. And yeah, I'm happy to take any questions.
Great, thanks, Andrew. That was a really good presentation, really thorough. Yeah, so if you've got any questions, put them either in the chat or you can raise your hands. Maybe while we're waiting, I could start. So more on, well, kind of the model selection and development.
Yep.
So I think over the summer you had someone looking at machine learning techniques. Did they improve the performance at all or not?
So that was specifically what I was talking about with the nonlinearity of, for various reasons at the start of my research, I sort of excluded that and wanted to look at a very interpretable and transparent model. And so, yeah, we had a master's student who's looking into what if we didn't impose that restriction. But the short answer is no. The nonlinear, like the machine learning models, which included an ANN, support vector regression, and random forest, did not show an obvious improvement over this model. Some of that may have been in, like, this model has been very carefully designed. and that was a bit more of a scattershot approach of let's try a couple of different ones. Or it may just be that at this level of like granularity of accuracy of perception responses that we've got, it doesn't really make a difference. So we'll probably be looking more into that as well, but for the moment, no, there's not an improvement moving into the sort of slightly more black box machine learning models.
Okay, cool. Yeah, and I noticed you hadn't, so you don't include any information about the respondents in the model. So you don't include, like, I don't know, some people might be more favorable to vibrant environments or something like that. Is that something you could include?
Yeah, so that I will say, since we've submitted this as a paper, that's actually exactly the comment we got from one of the reviewers. But in this case, it actually doesn't apply because we're looking at lockdown, applying this to lockdown responses. What demographic of people are we talking about for the lockdown? Do we have any reason to believe that there would have been a demographic change in that? How would we have incorporated that information into this predictive model? So it's just not, that information is already inherent in the data that we have. It doesn't really work for this application. That said, yes, that's true. Different people do have different perceptions, and that can be correlated with like demographic features. A previous piece of work we did, which also used multi-level modeling, did find that. We found gender and technically retirement status were the two most determinant ones. We believe that retirement status is actually just a proxy for kind of old age, that it's more about above 65 and under 65. But that's also some ongoing work now.
Okay, one more quick one before I let other people. So on the, you're saying you're planning to change from like location specific to sort of groupings of locations. Would you use something like k-means clustering, or just sort of more arbitrary, like this one's road, this one's park, this one's like, I don't know, other urban or something like that?
So the primary, the goal that I really want to get to is replacing this location ID here with kind of another regression model in a way. So instead of just a categorical location ID, we have like the visual openness as like an actual metric, plus some slightly arbitrary label of like architectural typology. Is it a square? Is it a park? Is it, you know, that sort of thing? Plus, I don't know, like time of day or something like that, right? So we have this list of attributes of the location, which goes straight into this model. That's the sort of goal. I'm still working out whether or not that will work. And if it doesn't, I probably will move over to some sort of clustering thing to where that cluster category goes in place of the location ID.
Great, thanks. So I see Navas, you've got your hand raised. Do you want to ask your question?
Hello, hi. Thank you very much for the presentation. It was very interesting. I was wondering if you have looked at between the difference between day and night. You know, the perception of soundscapes, because you know the visual cues are different. So, did you find anything in that?
We have not looked at that. Part of that is just a difficulty in, as I was saying, sort of the traditional methods of looking at soundscape. To do our surveys, we need people to be there, and we need them to be willing to be stopped on the street and asked a question.
So we don't have data at all for off the top?
Yeah, we just have during the day.
Yeah. Okay.
Yeah.
It's very interesting. I'll be in touch with you later. I'll email you. I have many questions, but I don't want to keep everybody. I really enjoyed it. Thank you.
Yeah, thank you.
Okay, well, I'm sure you can ask them if we have time. There's some in the chat, so I'll go through those. So Shiche asks, when you transition to Bayesian, will you test multi-level Bayesian analysis again, or just keep one level? Not sure if there is a difference when including randomness.
Yes, so it will still be a multi-level Bayesian analysis at the start, and maybe it'll come out as a flat model for eventfulness again, and maybe it won't. Part of what will change that is because we were applying this model directly to lockdown, we kind of started a bit early, right? When I started running the analysis for lockdown, I didn't feel that the model was really where I wanted it to be, but we needed to sort of start working on that. So where we're going now is trying out more features like the environmental stuff, trying out more and different types of acoustic features. So it'll be a new feature selection process. And so we're going to be starting again from the full multi-level model and redoing the feature selection process. So we won't be starting from this point. So the answer is yes, we'll be looking at a multi-level Bayesian model.
And Karen asks, are you exploring the same idea for indoor spaces?
So I am not doing any work on that at the moment, but a collaborator of ours in Italy, Simone Torsen, who I think, and Francesco can say more, will be coming and visiting for maybe like a couple of years at this point, soon. He has done work on indoor soundscape of essentially deriving that same circumplex for indoor, because there's different things that people find important. There's different descriptors for all that. So they've redone that and they're sort of moving forward. I don't know how much of this predictive modeling they're doing, but yes, there is ongoing work in indoor soundscape.
Okay, I don't see any more questions.
I think Duncan.
Did you have one?
Yeah, Duncan, did you just want to?
I'm in a room at the moment, so I can't ask it personally. But it was more about the like I noticed in the questionnaire when I carried it out last week, you had both positive and negative. So you said, would you describe this as eventful? And then later on, you asked if it would be uneventful as well. I'm just wondering if there's a difference between how people report positive and negative, because I guess that was the thing that I was surprised by in the survey, that you kind of asked both.
So just starting off at the beginning on that, the noise pollution stuff has traditionally focused on annoyance, right? So always just asking the negative one. They just ask, how annoyed are you, or how annoying is this sound? So Soundscape specifically is moving away from that and including the positive as well as the negative side of it. And that's the whole treating sound as a resource, right? It can make spaces better even by making them louder. Like, that's a possibility, which isn't true in an annoyance focused thing. As far as the second part of do these exactly correspond, right? Does pleasantness, high positive pleasantness, correspond with a negative response to annoyance, as in like they're saying not annoyed? We have looked at that. A paper we published last year by Matteo was looking at those sort of internal correlations and trying to see, do these match up the way that they're supposed to, and can we correct for that? And essentially the answer was they don't match up exactly. People scale the responses to those questions slightly differently. And so they're not sort of an ideal, not at all annoying is not necessarily the same as yes, completely pleasant, or vice versa, or anything like that. So there are some differences there. We haven't really considered that in this work. We're kind of taking the answers as is.
Okay, thanks for that. Yeah, That makes sense. Sorry.
All right, and I see Francesco's put a link in the chat for a paper on indoor perceived sounds, so that could be useful. Right.
Well, I will say, Kieran, as well, because I'm not working on this now, but before COVID, I was working with Worley on trying to do some of this objective modeling for office soundscapes, where the goal was to have sort of ongoing questionnaires and model the changes in the indoor soundscape to how people had perceived it, and do this over a time period. Unfortunately, that work was stopped because when we were planning to do office questionnaires, suddenly there was no one in the office.
All right, we're about out of time. I might just try and sneak in one last question.
I'm happy to stay over if people have more questions.
Okay, on your lockdown work, it's quite interesting that the sort of more pleasant places became less pleasant. Your hypothesis for this, is it something to do with it being like just a bit sort of less vibrant, or could it just be that the people answering it, because it was during a pandemic, they were in a, well, less mentally good state or something like that?
Well, the thing to remember with the predicted change that we're showing here is the lockdown perception is not people's actual answers. That's our predicted answers based on audio recordings. So essentially the way to think about this is you've got, for perception in general, you've got the physical inputs, right? The sound itself goes through some sort of perceptual mapping, and then output is their response. They're pleasant or eventful. We've replaced or tried to mimic that perceptual mapping with the model, right? So this is essentially the 2019 perceptual mapping.
Yeah.
We then take that model and feed into it 2020 audio, right? And so this is actually a really interesting thing about this work is there is evidence, or there is this thought that people's perceptual mapping, their response to sound would have changed, like even to the same sound would have changed because of COVID, because of the restrictions, right? And so it is kind of a thing that we're making this assumption that it wouldn't have, that this model holds between the two. And so we're kind of just saying, if 2019 people had been picked up and sat in these lockdown restriction spaces, how would they have perceived it? And that's what we're saying here. That's slightly different from if they had changed, if people were perceiving differently because of these lockdowns themselves, not because of the change in the sound, but because of the other, social, psychological stuff. That's a different question. And it's a really interesting question, but it's also much more difficult to answer, I think.
Cool. Right, I think we probably need to finish there unless there's any last questions. All right, thanks very much, Andrew. It's a really good talk and very interesting, and thanks everyone for joining. We should have another couple before the end of the year, so I'll let you know about the next webinars that we'll be having. All right, bye everyone.
Thank you.
Cheers.
Bye.